I'm missing? All right. We need the virtual icon strip because the real icon strip does not work. The technology lady could make it work. I couldn't make it work. So I gave up. All right. I think we're finally ready to roll. Okay, so all I need is a blank screen to write on, and away we go. So yesterday, Gauss's law says simply that epsilon naught times the closed integral of EdA, and this is a dot product of two vectors, is equal to the charge enclosed by a Gaussian surface. So when you're solving Gauss's law problems, you look for symmetry. You want to use the symmetry in your favor to keep from having to do a nasty, nasty, nasty integral. This entire chapter, the name of the game is avoid doing integrals that would give you nightmares otherwise. There's lots of different symmetries that occur, and I'll go through a few of the classic ones, and if you've read the book, they go through them too, but I kind of want to, step through this with you and kind of show you how this crazy thing works. It's beautiful, it's weird, and if you understand what was in that video, it's really easy. Okay, so first we start with spherical symmetry. So let's see. I kind of did this differently than in my notes, so we'll say spherical symmetry. And I'm going to start with a thin shell of charge. So I've got a non-conducting, actually it doesn't matter, but let's say it's a non-conducting thin spherical shell. It's a ping pong ball. It's got radius r. And it's got a charge on it. Okay? Now, we have the advantage of already knowing the answer. We know how to find the electric field, bless you, around and inside this thing. So inside a thin shell of charge, what should the answer be if we try to find the size of the E field? 0. Inside the shell anywhere, the center but anywhere, should be 0. Outside, we found the E field by treating the shell as a what? As a point charge, yeah. So, yeah, when we did gravity, we treated this thin shell as a point mass. Now we're doing electrical forces, so we're going to treat the thin shell as if all the charge were located at the center, as long as we're outside the shell. So we know the answer already. And so we're going to apply Gauss's law and get the answer again. So either you're going to say to yourself, Gauss's law is true and this is confirming what we do, or you're going to say this is a test of Gauss's law to see if it really works, because we know the answer. All right, so if I would like to know what the field is like right there, they say at point P, what's the field? What you do is you draw a Gaussian surface that's symmetrical to the situation. So in this case, the Gaussian surface is going to be a sphere whose radius is smaller than big R, centered on the center of the thin shell. So my Gaussian surface, and again, when my holographic board comes in, I'll be able to, I missed a little due to the delay on the, but that point is supposed to be on the shell. When my holographic board comes in, I will actually draw spheres and not like cross sections like they are. Okay. So, we applied Gauss's law to this, which is right up there. Epsilon naught closed integral of EdA equals Q enclosed. Okay? Because of the symmetry, we're going to claim that E is everywhere the same along the surface of that sphere. So again, we can pull out the E. Okay? Now, we don't have to go much further because what is Q enclosed? How much charge have we enclosed in our fictitious shape here? So I put this Gaussian shape. It's an abstract entity, right? But imagine I have this little sphere inside of my spherical shell. How much of the shell's charge is enclosed in my Gaussian surface? 0. There's nothing trapped inside it, right? There's no charge inside. So that means, according to Gauss's law, if this is 0, then dA is obviously not 0. Epsilon naught is a constant in the universe, therefore E equals 0. So it's that simple, folks. According to Gauss's law, if there are no enclosed charges inside your Gaussian surface, then the E anywhere on that surface should be 0. Okay, so this is a case, by the way, this is little baby r, and the case where little baby r is less than big R. Okay? This is like part 1. Part 2. What if it's a point outside? Now we know the answer, yes, but if I had a point outside and I want to apply Gauss's law, I want to find a shape that intercepts that point, and I want it to be such that every point on that shape has the same electric field strength. So I want it to be symmetrical. I'm going to use that symmetry to make my integral really easy. So once again, it's going to be another sphere encompassing everything. Okay? And at that point, a certain distance away, so now R is bigger than the radius of the shell, and I would like to know, okay, what is the E field there? How you guys doing out there? It's so easy you think you're missing something, right? You think, oh, this has got to be harder than this. It's not. Okay, so we set up our integral. We say, okay, epsilon naught E dA equals Q enclosed. By the way, I forgot to mention, let's say the charge on our shell is Q. Okay? 2 questions. Number 1, would E be the same everywhere on our imaginary shell? Absolutely. So I can pull it out. Second question. How much of big Q is enclosed by our imaginary sphere? All of it. So I really should write at this point, let's see if I can do a quick erase here. I could really say, all right, since the enclosed charge, the charge enclosed by my shape is all of it, and that's what I'm going to put there. And this integral, which I forgot to make it a closed integral, that's the sum of all the little pieces of the area of my sphere, which is always just, in this case, the surface area of a sphere. So this becomes epsilon naught E 4 pi r squared. I beg your pardon, again, Mr. Evely, find the eraser. Okay, r squared equals q. So if I solve this for e, which is what I'm after, I get q over 4 pi epsilon naught r squared. Sometimes, instead of saying 1 over 4 pi epsilon naught, we have said k. No problem. So what Gauss's law is telling us is that we can treat this sphere as a point charge, because the E field of a point charge is kq over r squared, where r is the position of the point charge, in which case r tells us how far away we are from the center of the sphere. All right? So 2 results. One for r inside the sphere, one for r outside the sphere. Ta-da, we win. Now, one thing that I want to say always, but not always, but most of the time happens on the AP test, is they will say, all right, now draw us a graph. It's slightly irritating, but they always do. Almost always do, and say, okay, here's E, here's all the different radii, and let's say this is the radius of the shell. So if we were to draw a graph of this, we'd say to ourselves, what is the E field from 0 radius to the radius of the shell? 0. So our graph is going to be really boring. What is the E field from R to infinite R when we're outside of the shell?
Small.
It gets smaller and smaller and smaller from some initial value, right? So we've got some initial value, and then it's going to go, inverse R squared, asymptotic toward 0. So it's a goofy graph. There's a definite disconnect right there at the surface. As soon as you leave the surface of the sphere, whoa, there's an E field. But then as you pull away, it varies with the inverse R squared. So, yeah, no. And then if they said, okay, what's the value right here where this starts? You'd say, oh, I know what it is. It's kq over big R squared. It's right at the surface. Because they usually want you to label the special things happening on the y-axis. There it is. I kind of had my E in the way there. All right, so there's that mess is our first example. Second example. Now, if you need to see this again, it will be on YouTube, so, I'm going to be famous soon, as soon as someone will discover these videos and say, oh my gosh, he's better than Khan Academy. Not really. Bill Gates poured all kinds of money into Khan Academy, and it actually kind of sucks. Boy, I'm going to put that on YouTube. Shoot. If you watch it, it's okay, but people are coming up with some alternatives to Khan Academy, and I'm kind of interested to see what they come up with, because Khan Academy is okay, but he's not a physicist, at least the videos I saw a couple years ago. And so he makes mistakes that are subtle, and those are bad mistakes to make. I mean, if you make big glaring errors, students can go, oh, I see, he messed up there. But when you make subtle mistakes, students are like, they just put that as part of their thinking, and they move on. It's like, oh, no, don't do that. Don't do that, dude. You don't want to do that to kids or adults or anyone watching. So they're not bad. It's just, helps to have a degree in physics when you're trying to teach physics sometimes. All right. Next, what happens if we have a solid sphere full of charge? Okay, so here we go. Non-conducting Okay, you want to talk like a physicist. Non-conducting solid sphere with uniform charge distribution. Instant translation, a bowling ball. And we add some charge to it, and that charge is evenly spread throughout the sphere. Okay, it's got radius, capital R again. And I'd like to know what the E field is like both inside and outside the sphere. Predict. What do you think we're going to get outside the sphere? We can treat that sphere as a what? It's going to be a point charge again, right? Because just like the shell, we can treat it like a point charge if we consider the bowling ball like a series of concentric shells. We can treat them all the same. So I'll do that first one and say, okay, I'd like to know what's the E field right there. And so I make a shell around it using the spherical symmetry. I can't talk. And our equation for Gauss's law pops up into your head. And you say to yourself, E is going to be the same everywhere on that dotted line. If it is, I can pull it out. Are you noticing some repetition here? By the way, I'm also going to say the total charge is capital Q again. Okay. Once again, area is just the area of our Gaussian sphere, 4 pi r squared. Okay, once again, I'm going to call that little r. And you notice that the result is exactly the same as before. E equals 1 over 4 pi epsilon naught. I've got a Q on top. I've got an r squared on the bottom. If you want to call the 1 over 4 pi epsilon naught K, be my pest. And we win. Next, the hard one. What about inside the sphere? So this is R greater than big R. Now we're going to do R less than big R. We did this with gravity. So this is not new, except that we're doing it with charge and we're using Gauss's law. Now I'm going to switch colors real quick because if we're inside, we want a Gaussian surface that has a radius smaller, and I filled that sucker with charge, so it's going to be hard to see. So I'm going to say, all right, now I've got radius r that's smaller than big R. Let's do this. Okay? Here's the difficulty. Q enclosed. How much charge is enclosed by that imaginary sphere whose radius is less than big R? How are we going to do it? How are you going to find the charge enclosed? I'm looking for one word that will make this possible. It begins with a D and it rhymes with density. Density. Ever see Back to the Future 2? I am your density. He meant to say, I am your destiny, but he was a little nerd, and so he walks up to the girl and says, I am your density. It was fun. But anyways, back to this. Remember, volumetric density is going to be rho, which is the total charge divided by the total volume. Or it can be a piece of the total volume encloses a piece of the total charge, and that should give us the same answer. So I'm going to say Q enclosed over this inner volume, inner. So because we're talking about density, it's a characteristic property, I could take the whole charge divided by the whole volume and get rho, or I could take the little bit of enclosed charge divided by a little bit of the volume that's enclosing it and get the same answer. So that means I can say Q over 4/3 pi big R cubed is equal to Q enclosed over 4/3 pi little r cubed. Are we all on the same page? You okay? And when you look at that equation, you say to yourself, why, right? Why? Now, what I'd like to know is what's Q enclosed. So what do you do now? No yawning, Gardner. This is too exciting. Can you solve that for Q enclosed? In your sleep, right? So you're going to say, hey, Mr. Emily, Q enclosed is going to equal big Q times little r cubed divided by big R cubed. Okay, I didn't put that in the best spot possible. This board kind of limits my area. So let me proceed this way. Those watching the video will have to deal with it. And we're going to say, all right, epsilon naught, E on this inner sphere is going to be the same everywhere by symmetry, so I'm going to pull it out, leaving me with the integral, closed integral of dA is equal to big Q little r cubed over big R cubed. The closed area, I beg your pardon, the closed integral of the area is just going to be the area of my inner sphere. So it's the area of this blue sphere here, and I'm going to claim that the surface area is 4 pi little r squared. Okay, we do a little y-nation, y, and solve for E. Okay. Have I made any awful mistakes? Looks pretty good, doesn't it? Again, if you want the 4 pi epsilon naught out of the bottom and just put a K on top, feel free. The AP folks, it was confirmed online. I'm part of the AP listserv, and they ask lots of questions like this, especially when we get to this part of the year. And the official answer was, no problem. K all you want. There are times you won't want K. That's why we do this. So, question. If they asked us to draw a graph, okay, here's again where I wish I had a little more area to play with. We're kind of done with the diagram, so let's see. Oh, it's kind of sad to lose the diagram. I mean, I should have gotten rid of the other stuff. Okay. So here's E, here's R, and here's the radius of the sphere. So if we're inside the sphere from 0 to R, here's the equation down here. We just came up with it that controls the E field, that tells us what the E field is like. What kind of equation is that? Power law, quadratic, linear, exponential. What kind of equation is that? Did you say direct proportion, sir? You are correct. Because, check this out. Is Q a constant or a variable? Constant. I'm not changing the charge on the sphere as I go, right? 4 pi epsilon naught, those are all constants. R, the radius of our sphere, was that constant? I'm not talking about the Gaussian sphere, I'm talking about the actual sphere. The bowling ball. Was the bowling ball's radius constant? Oh yeah, baby. The only thing we changed was R. So as we move R from 0 to big R, you're right, it's a direct proportion. It's nice and linear. E changes with R without any exponents or square roots or weird things. It's just linear. Then what happens to it? We hit the radius of the sphere. Now we're outside the sphere. See, I shouldn't have erased it. So here's R. So first we're inside. We go dot, 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 dot. Now we're outside. What's happening as we move away from the sphere? If we treat the sphere as a point mass. We've seen it before, right? I see your hands, Elaine's hands are going, Allie's hands are going, now I'm stuck. I'm calling you that. That's bad. All right, it's not bad. But. Okay, so it's doing that. Okay? Do these actually meet up right here? Is that actually a thing? That the linear line and the exponential, sorry, that's not exponential decay, the inverse R squared decay actually meet up at that point to make a little cusp? Check it out. And the bottom equation here, turn little r into big R. What do you get? When little r equals big R, yep, you get this guy, right? Yeah, you get this guy back. So they do agree. At the surface, they agree. So it goes higher, 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 reaches a maximum, and then whoa, and leaving that non-differentiable cusp there. There was talk about those in calculus. Never saw one in real life, I bet. Cusps. Don't give me that look. Did she ever say the word cusp in calculus? Oh, okay, good. All right. I'm not crazy. So I taught calculus, but it was like 20 years ago, so things have changed, I bet. Right? Calculus evolves and changes. Not really. No, it's about the same. All right. Okay, now we're into some stuff the other hour didn't get to yesterday in 0 hour, so now you get some new stuff. Are you ready? We've gone through like 4 Gauss's law examples. Are you hanging in there? Yeah. Yeah, this is pretty intense. But so far, it's not that hard. This is the hardest thing we've done, is deal with this crazy density stuff. Okay. Yeah. Okay. Whew. Okay. Suppose we've got a line, like a string or something, and it's really, really, really long. And we put some charge on it. And the charge density, remember, is charge per unit length. So we've got this infinitely long string. It goes up infinitely far, down infinitely far, and it's got a uniform charge on it. And the question is, what is the E field like right there? How can we figure that out? So let's follow the steps. First step, consider Gauss's law. Okay? Remember, our goal is to create some symmetry so we can pull E out of the integral and make our lives much easier. So, what would our shape be? What would we use to enclose a portion of this line? Because we can't make it an infinite shape. That would be really disgusting. So you're going to have a finite shape, but it's got to enclose this line so that everywhere on its surface, the E field is either 0 or the same everywhere. A cylinder, you say? Because I wrote cylindrical symmetry up there. Dang it, I should have done that, should I? If I was going to ask that question. Okay, so I'm going to take a cylinder, and here we go. Little artistic flair. All right, so this is the imaginary cylinder, doesn't exist, that we're going to wrap around this long string of charge. Let's say the cylinder has a radius r. Now that is the same as the distance from the string where we want to find our E field. So the E field that we're looking for is sitting on the surface of this, the lateral surface of this cylinder. The length of the cylinder is L. You can see where that's going, right? Look up at the density equation. Okay. Again, everywhere on the sides of this cylinder, all the way around, is the E field the same everywhere on that surface? Because we're the same distance from the line, and it's symmetrical. So it doesn't matter where we are, as long as we're the same R from the line, we're going to experience the same E. How much E are we going to experience on the top face or the bottom face of the cylinder? Okay, let's draw some E field lines. This will help. So let's make E field lines like green or something so we can see what's going on. Okay, these are positive charges, which means the E field lines go in all directions, but away from. Okay? So again, when my holographic board comes in, I'm going to draw them out of the page too. But check these out. Field lines cannot cross each other, and there's field lines coming off of every one of these positive charges. Okay? So my question to you is, how many field lines are crossing the top of this cylinder? Hmm? None. Okay, so here's a cylinder. There it is. Something that's doing this. Okay, whether it passes through the cylinder or over the top, is not crossing it. Now, what you were thinking is, suppose it grazes it. You know, what if it's like, zips right across the top of the cylinder? But remember, flux is perpendicular. So what we need is, when we're finding flux, we're saying, or better yet, okay, so if I go E times A cosine theta, and here's the area vector, and here's the E field, you'd say 0. It's not really penetrating that surface with any angle other than 90 degrees. So it doesn't matter. So the top and bottom of the cylinder don't matter at all. All right, and I've lost the magic. Okay, there it is. Okay, so let's do it. E is the same everywhere. No, I don't want green anymore. There we go. E is the same everywhere, so pull it out of the integral. Ooh! We got to replace Q enclosed. With what? How much charge is enclosed by my cylinder? Look at my density equation. Lambda L. So I'm going to say lambda L. Okay? And I'm going to replace the integral, the sum of all the area on the sides of this cylinder with what? What's the lateral area of a cylinder?
Length times width.
Yep. So she said it. 2 pi r, the circumference divided, or sorry, multiplied by the length, right? So we're going to say the distance around the circle multiplied by the length of the cylinder will do it. So I'm going to say 2 pi r times L. And I want to solve that for E. What's the first thing you do before you solve for E? Wah. And then you can say, okay guys, E is equal to lambda over 2 pi epsilon naught, and we need an R down below. And by the way, if you want to get rid of the 2 pi epsilon naught, one way to do it is to multiply the top and bottom by 2. Because if I multiply the top by 2, the bottom becomes 4 pi epsilon naught, and I've got 2k lambda over r. So if you like that better, you know, be my pet. All right? So how would this solution change if the charge were negative? I have all positive charges on that string. What would happen if they were all negative?
Be the same but opposite.
Be the same but opposite, yeah. So I wasn't trying to trick you. All the field lines would be going in, so we'd have a big old negative sign on our answer, and that would be it. Does it make sense to you that the length of the string canceled out? The length of our cylinder, sorry, it's not the length of the string, it's the length of our Gaussian cylinder. Does it make sense to you that it canceled out? Should the E field there depend on the length of an imaginary cylinder we put around the string? No. It doesn't matter where we are on this string, as long as we're the same distance from it, we're going to experience that E field. Okay? This is hard to see, but these lines actually are spreading apart, but you'd have to look at it from above to see it. So if you look down from the top, you would see these guys radiating out. So at first, just looking at the picture, you'd say, okay, why is it changing? These guys are all parallel to each other. But when you look at it from above, if this is the string going into the board, wait for it to catch up with me, then the E field lines are doing this. So looking down on this infinite string from above, you would see, oh, they're all, they are separating. So at first you think, why is there an R there? Because these are all parallel. Oh, they're not. In the other dimension, they're not parallel to each other. Okay. Oh my goodness. All right, last one. Can you handle one more? You gonna make it, Beak?
Yeah.
This is a long hour, isn't it? There's a lot of stuff. It's not hard, it's just a lot of stuff. Go away. Okay. Last one for today. What Roman numeral am I on? 6? 6? All right, let's go. 5? Okay, that sounds better. That's okay. Okay? And these are all things you encounter every day in your life, right? So just the other day I was driving along and encountered an infinite sheet of charge. No, they're mathematical oddities meant to make a point. Okay, so we've got a really thin sheet, really flat, thin sheet, and it's got a uniform charge distribution. In your notes, you probably have somewhere that the uniform charge distribution on an area is charge per unit area. Okay, so this sheet actually goes on forever and ever in all directions, and I would like to know what is the E field like above it at some point. So at this point right there, what is E? Now this is a puzzle. What shape would we use to do this? A cube might work. Yeah. If we put a cube, if we set a cube on that sheet, the sides that are perpendicular to the sheet wouldn't have any E fields penetrating it, right? They would only go through the top. So that would actually be, and the bottom, thank you, because that would be a really good idea, actually. What they do in your text is they put a cylinder on there. So almost the same. Well, what it does is it reduces some of the craziness of the corners and everything. It gives you even more symmetry. So I'm going to go ahead and use the cylinder. So I'm going to need a different color for my Gaussian shape again. Let's go blue again. So what I'm going to do is this time the cylinder top is where my charge is located, or sorry, where the point is located where I want to know what the E field is. And I'm going to have that cylinder go down to the surface of the sheet and keep going the same distance on the other side. Okay? Your suggestion of a cube is a good one, but this will offer us even more symmetry. And what are the field lines doing here? They're going up and they're going straight down. They're parallel to each other. It's a beautiful thing. So field lines are going to look like this. They're going to shoot up from the sheet. They're only penetrating the ends of the cylinder now. Okay? So penetrates this end, penetrates this end. Okay? Gauss's law. Okay. So again, the sides of my cylinder, I can ignore. No E field lines are passing through them. They're all parallel to those sides, and some might skim across the side, but we don't care. Nothing's penetrating at an angle. The only surface that is getting penetrated by the E field would be the top of that cylinder and the bottom of that cylinder. Okay? So what we're going to do is we're going to say, all right, well, the E is going to be the same, clearly, here and here, though in opposite directions. So we're going to say, all right, I wrote this in kind of an interesting way. What if we pull this guy out? And for now, I'm just going to call this the area of one end. And so the E times the area of one end plus the E times the area of the other end is equal to Q enclosed over epsilon naught. So the point I'm making is we've got E going in two different directions, and we kind of have to pay attention. So if those E's are actually the same in magnitude, and those areas are clearly the same, I can say 2EA equals, wait a second, what's the charge enclosed inside our cylinder? It's only the charge sitting on the surface right here, enclosed in that cylinder. How are we going to do that? We're going to say the Q is equal to sigma A, right? Whatever that area is. This area here is, so we can't take both sides. What I'm saying is, watch it. You know, we've got these two. We're just going to deal with that area. And so I'm going to say sigma A on top, epsilon naught on the bottom. So notice I didn't replace A with 2 pi, pi r squared because, we lose it. So E is equal to sigma over 2 epsilon naught. And that's it. That's the whole story. Okay, notice no distance. E is the same no matter what distance we are from the sheet. We could be 1 millimeter or 5 miles away. It doesn't matter. Why? Those E field lines are parallel to each other. Yes, ma'am. Okay, so I've had you do problems 1 through 3. I would like you to continue along those lines. In 23-4, there's the Gauss's law of concepts. I'd like you to give these a try. Remember from yesterday that the amount of flux coming off a point charge is just Q over epsilon naught. And it doesn't matter whether you have a sphere around it or a cube around it. So I believe it's 5 puts a cube around a charge. But how much flux is running into that cube? The same as for a sphere. And then they say, how much flux through one face? Well, if there's the same amount of flux going through each face, and there's 6 faces, you know what to do. Then I'd like you to do 19 and 20, because those are dealing with the conductors. And then I'm going to have you do the cylindrical symmetry. So 24, 26, and 29. Okay? Sorry about that. You had a night off, but we have to catch up a little bit. Next week we'll deal with planar symmetry and spherical symmetry, and we'll be fine. Do your best on those. Give me a call if needed, or pop me an email, because all day Saturday I'll be at the robotics center. But if you pop me an email, I can give you a call if you just, say, Mr. Everly, give me a call when you need to, right, when you have a chance. All right? Thank you so much for listening.